Good morning, viewers. Hope everyone had a nice weekend. I've got two dogs right here. Snoozing right next to me. Bugger. Hazel. I'll wait about 30 more seconds and then I'll get started. Okay. So, today we are going to be learning about a little bit about scientific computing. So we're going to continue with the Apache Commons Math API, and so one of the most common things now, if you didn't know, I'm also the physics teacher on campus, and so I have a special interest in physics. And so we're going to kind of go into that realm this week, a little bit into the realm of physics, or at least into the realm of scientific computing. Now, one of the most common problems that you have to solve in science in general is something called a differential equation. Okay. And so differential equations, very, very common in science, okay? And so I'm just going to give kind of an introduction to what a differential equation is. I haven't checked to see how many of you are in calculus, but I'm not really going to explain this in terms of calculus. I am going to use some calculus symbols, but I'm going to explain it in plain English, okay? So the first example that we are going to use is I'm going to let a variable y equal the population. So for example, the number of humans, okay? And then the population, y, is a function of time, okay? All right, so I could put parentheses t, like f of x, okay? So the population is a function of time. All right, And so there's a special symbol to indicate the rate of change of a variable. So in this case, the rate of change of the population. Okay. So, and that's to put dy dt. Okay. So what this is the rate of change of y with respect to time. Okay? The rate of change of y with respect to, or I should say t. But let's think about what y and t are representing, okay? So y is representing population, and t is representing time, okay? So this is like, so if we are thinking about the human population, then y is the number of humans, and then t is time. So maybe t is time measured in years. So we could interpret dy dt as the rate of growth of the population. So maybe it's like, I don't know, 200 million people per year. I'm not sure what the how quickly the population increases. Okay. So that is how. So we're going to be using these two symbols a lot in the next 2 lessons at least. So now we can get to what's called a differential equation. All right. And so a differential equation is an equation that's of the form dy dt equals a function of y. All right. So that's a basic differential equation. All right. So the so this is in general what a differential equation is. But let's talk about a specific differential equation. Dy dt equals a times y. All right. So this equation is representing what we would call, or this is like the exponential growth equation. Okay. This equation is representing exponential growth of the population. All right. Why is that? Well, what you can see is that the rate of growth of the population is equal to A. A is just a random constant. Okay. That constant, and then, so dy dt is equal to a constant times the size of the population. So what that means is that the bigger the population is, the faster the population grows. Okay? The bigger the population is, the faster the population will be growing. Okay? And then the constant A is kind of representing, like, how many people choose to have babies. Okay, so if A was really small, then that means that not a large proportion of the population chooses to have babies. But if A is really big, then a large portion of the population has a lot of babies. Okay, so that's an example of one. Now this equation is really simple, and we can solve it no problem. If you know calculus, you can solve it no problem. But I'd like to talk about something that's a little more realistic, because in reality, you can't just have exponential growth forever and ever. Okay, so if we were to graph, if you were to graph the solution to this equation, all right, if you were to graph the solution, y as a function of time, it's exponential growth. Okay, but that's not realistic. Okay, it should have a slope, something like this. Yeah. Because there are finite resources. Okay. So that's, yeah, so you can't just have it grow forever and ever and ever. Okay, because eventually the population will be competing for resources, and there won't be enough resources for everybody. So eventually what's going to happen is the population will level off. Okay, so but this equation doesn't model that. This equation just has perpetual exponential growth. Okay, so let me introduce another equation that's very closely related to this one, and this is the one that we're actually going to simulate. So dy dt equals ay minus by squared. Okay, so it's exactly the same first term. So this is basically, see how it's a positive term? So this is basically people being born. And then this term is minus. So this term is basically people dying. So we have rate of birth, rate of death. Okay. And you could look up this equation. It's called the logistics equation. It's used in biology a lot to understand populations of creatures. And so, anyways, so you know, if you look up the equation, they will derive, you know, why is the death rate proportional to y squared? Okay, for example. All right, so one of the interesting things about this is we can use the equation to determine the steady state population. Okay. Okay, we can use the equation to determine the steady state population. All right, so when I say steady, remember how I said that the population is going to level off at some value where the birth rate and the death rate are equal to each other. Okay, so like for example, humanity has not reached that point yet. Our population is still growing, but you know, there are other creatures where, you know, they have reached their maximum population or their steady state population. Okay, and you know, one thing that I want to point out is that these constants a and b can change. They're not truly constant. So for example, if we, you know, if there's deforestation, and that's going to reduce the amount of resources for animals in a jungle. And so that in turn is going to raise the B value for that population. Okay, so if we want to find the steady state population, that's the population where the rate of growth, where it's no longer growing. Okay, so dy dt equals 0. And then, so that's the left-hand side of the equation is 0. So we have 0 equals ay minus by squared. Then I could add by squared to both sides. So I have ay equals by squared. And then I'm going to divide both sides by by. The y's cancel out here, the b's cancel out here, and then one of the factors of y cancels on the right-hand side. So I have a over b is the steady state population. Okay. Anyways, so we haven't even really talked about programming yet. I wanted to spend a little bit of time just saying what is a differential equation. Okay, so now we're going to go to the actual programming. So let me just let me just show my desktop here. So I'm on the Apache Commons Math webpage right now, and this is called an ordinary differential equation. And solving that equation, so in other words, determining the population as a function of time, is what is called integration. Okay, so it has an example, and I basically wrote down, or I modified the example to suit my own purposes, but this is basically where I learned how to do the Apache Commons Math integration. Okay, so let's look at the actual code. Okay, so I wrote a class. It's called Commons Math 2, and it's going to be implementing, so remember that's an interface. Whenever you see implements, it means that's an interface. Okay. First order differential equations. All right. So the interface must have, so if you recall what we learned earlier, an interface must have certain methods. Okay. And those two methods that you have to have are get dimension. So this is part of the interface. All right. And then also compute derivatives. This is also part of the interface. Okay, so those are the two methods that are part of the interface. All right, so so the first thing we have is, if we look at this class, we've got a field which is an array of doubles. Okay. And so we are going to have C of 0, the 0th part of the array C is going to be equal to A. All right. And the first element, the 1th element of the array is going to be b. Okay? And then we have a constructor, which is right here. And the constructor basically takes in an array, a double array, and then initializes the value of the field. Okay? Now, what is the getDimension method? It returns an integer. And so for this particular problem, all we're doing is we're solving for one function, which is the population. Okay? But as we'll see later on today, but then also in the next lesson, we could have multiple functions that we're trying to solve for simultaneously. So the dimension is basically the number of functions that we're trying to find. Okay? And since we're only trying to find the population, there's only one value. Okay? So that's why we return 1. And I have some stuff commented out, okay, because we're going to do 2 examples today, and I didn't want to type it out on the fly. So if I look at compute, so the second method that we have to have is a void method called compute derivatives, and it takes in 3 arguments. A double called t, all right, and so t is of course time. An array of doubles called y, and these are, remember, we're not limited to solving for just one function. Okay, so our array of values for y is basically only has length 1 because we're only solving for the population. All right, so we only have, so basically the length of this array is equal to the dimension of the problem. Okay, so so we don't even really need to do an array per se because it's only 1, but the way that the interface is written, it has to be an array. And then the y dot is such that this is the rate of change of the corresponding element of y. So for example, y dot 0 is equal to dy dt, the 0th part of that, okay? And then similarly, you know, if we had more than one function that we were solving for, y dot of the one element of y dot would be the derivative of the one element of y, the rate of change of the one element of y, etc. Okay? So, if we look at our, let me go back to my piece of paper here. So if we look at our differential equation right here, as I said, dy dt, all right, is what we would call y dot, all right, and then we said a is basically going to be c0, so we have c0 times y minus, and then b was basically c1 times y squared. So in the programming language, this is the form of our differential equation. So it's basically we're changing around the variables a little bit. Okay, so going back to the program, you can see that that's exactly what I typed into this equation here. So this is the logistics equation. Okay. So you can see it says y dot equals c0 times y minus c1 times y squared. So then I have my main method. Okay. And so the first thing I do is I define an integrator object. So the integrator object is the object that solves the equation. Okay, and so this solves the equation. All right, this object does the, and so you can see it's some, so I'm going to give you the file and you're just going to copy this line. But the object is called DP853. And the reason it has that name is because this is the algorithm it's using for solving the equation. So if you look on the Apache Commons Math, it has a lot of, these are different, see it says available integrators, so available solvers. And it has a variety of different algorithms. And we're just going to choose this one, all right, because that was the one that was in the example. But this is a really big field of different algorithms that solve this kind of problem. Okay, and then, so that's the first thing I do is I create the object that is going to solve the differential equation. Okay, and then I create a differential equation object, which is the Commons Math class itself, first order differential equation. All right. And so it says first order differential equation ODE equals a new Commons Math of a new double. And so remember, these are the coefficients of that. So we're going to have A equals 1. Actually, let's have A equals 5 and B equals 2. How about that? So this is A. This is saying that A equals 5, B equals 2. Okay, and furthermore, that means that the steady state population is going to be A over B, which is 2.5. All right, so we're going to use that as a check to see that the integrator is actually doing what we want it to do. All right, so then I define a double array Y, and the double array Y is what is called the initial condition. Okay, and so you can see that the dimensions of Y has to match the get dimension. Okay, so what this is saying is that the initial population, is equal to 0.25. All right. Now that sounds goofy because you can't have a quarter of a human, but maybe it's the population measured in millions or something, so it's a quarter of a million. All right. And then Z is an array that will hold the answer. I have to define the array before, okay, so it's not going to spit out the answer. So I have to basically, I have to define where the answer is going to go before I ask for the answer from the integrator. Okay. So now I have a for loop, and it's going to iterate 100 times. Actually, I should do this 101. This is going to iterate 100 times, and you can see that it's using the integrator object. So we are calling the integrate method, and remember, integrate is the name for solving it, of the integrator object. So we're saying do your thing, and we feed it in 4 arguments. Okay, so I will put those arguments on the next line. So the first object is the differential equation object. That's the first argument of the method. Okay. The second argument is the initial time. Okay, so we're starting at time 0. The next argument is the initial conditions array. So that was y. So we were saying, remember, that the initial population was 0.25. Okay. And then this is the time at which we want to get the solution. So the final time, if you will. All right. So, and we haven't said what the units of time are. Maybe the units of time are years. Okay. So you can see that when I equals 1, that's going to give us 1/20th. Okay. So basically that's 1/20th of a year. I'm getting the population after 1/20th of a year. And then z is where the answer goes. All right. So there's 1, 2, 3, 4, 5 arguments to that method. And then what I'm going to do is I'm going to print z. All right. Because remember, z is where the answer goes. So I'm going to print where the answer is. And I'm integrating over this 100 times. So I'm finding the population at a certain time, and then I'm finding it at another time, and then another time, and then another time, and then another time. So I'm going to be printing out the population at 100 different times. So let's compile it. All right. And then let's run it. Cool. So this is working really well. Okay, so here's the first time that it computed. Oh, here's the first time that it computed the population. So we can see that the first time is slightly above 0.25 because 0.25 was the initial population. So here it's starting to grow. Okay. All right. And it grows. And you see how it approaches 2.5. Okay? So this is that's called the carrying capacity. So the population is reaching its carrying capacity. All right? So basically we're printing out numbers of what happens as time goes on. All right? Now what if I had started above the carrying capacity? So what if I started with a population of like 4? So what if the initial population was 4? And we know that the carrying capacity is 2.5. Well, what's going to happen is basically there's not enough food, and so people will die until there is enough food. So we're actually going to see, so if I run this, you can see that it immediately starts dropping below 4. And now the population, so these are all the people are dying until we get down to about 2.5 again. All right, so that's pretty cool. I mean, it's not cool that our simulation had people dying, but it's cool that we were able to solve the problem. Okay. So we're going to learn about one more differential equation today. And so this one comes from physics, all right? And this equation is dv dt, okay, equals C, I'm going to call it C0 minus C1 times V. All right. So this equation appears in terminal velocity problems, okay? So what is V representing? This is, V is your speed, okay? And so this is the rate of change of your speed. How fast is your speed changing? And so when you are, so this term is representing rate of change of speed, okay? And then there's a constant term. So there is a force that is acting on you, okay, called gravity, and it is pulling you downward, okay? So it's if you drop something, right, its speed is going to increase, all right? So this is the effect of gravity. Gravity causes your speed to increase at a constant rate, okay? So this is modeling a skydiver, by the way. Modeling a skydiver. And then this term, now skydivers don't just speed up forever, all right? A skydiver achieves a maximum falling speed. Why is that? It's because of air resistance. Air resistance, as they start to fall faster and faster, there's more and more air resistance, and eventually gravity and air resistance balance each other out, and you just fall at a constant rate, okay? So this term, notice how it depends on your speed. The faster you go, the more air resistance there is, okay? All right. And then, so this term is representing air resistance. Okay. Now here's the thing. Okay. V is the rate of, so dv dt equals rate of change of speed. All right. But V is equal to the, so what is your speed? Your speed is equal to the rate of change of position. Okay? So you have, so basically this is acceleration, and this is speed. Okay? So your acceleration is the rate of change of speed, and your speed is the rate of change of position, of rate of change of how far you've fallen, okay? So these are actually going to be our two equations. So we're going to have dx dt equals v, and then dv dt equals c0 minus c1 v. So we have, notice how we have two functions. So we are solving for x and v. All right, so that means that the dimension of the problem is 2. Okay, so let's go back to the code. So we are not doing the logistics equation example. All right. PU, Hazel. My gosh. We are doing the Skydiver equations. So these are the Skydiver equations. All right. And so this first equation, so we're going to have y0, the 0th component of y is going to be equal to position. And then the first component of y is going to be equal to the speed. All right? So the first thing we have is, notice how this equation right here is saying that the rate of change of the first component of y is equal to the rate of change of the 0th component of y is equal to the first component of y. So this equation is dx dt equals v. That's what that equation is saying. Then the second equation is saying the rate of change of y1 is v, so this is saying dv dt, dv dt equals c0 minus c1 times y1, and we know that the first component of y is v. Okay, so what I want to point out is that this is exactly the same as these two equations that are modeling the Skydiver. All right. So going back to this, again, oh, and I also have to change the dimension of the problem to 2. So I'm going to return 2 because now I have two variables, remember, x and v. And so I still have c0 and c1. All right. So here I have c0 and c1. I'll just keep them the same. But notice I have to make some changes here. Okay, this isn't going to work anymore because there are the array y. I'm solving for two functions, so I have two initial values. So what this means is that the initial position is equal to 0, right? Because that's what this first one is. Right, because y0 is x, and then the initial speed is also 0. So those are the initial conditions, and then the array that holds the answer has to also have 2 dimensions because I'm solving for 2 functions. Okay? And so then I just do the exact same thing. Okay, so this is just boilerplate. It's going to be exactly the same. And I'm printing the 0th component of the answer. The 0th component of the answer is going to be position. So I'm printing the position at various times. Okay, so let's run it. Spits out some numbers. Okay, so what do we have? Well, we start out at position 0, so you can see that the position number starts out close to 0, and you can see that it's increasing by about very small at first, okay? But you can see that as it builds up speed, the position starts to grow faster and faster. Okay, so the position starts out, it only grows by a tiny amount. Okay, by like 0.02 or so. And then down here, it's increasing by 0.1. And then if we go down here, it's increasing by 0.14 or 0.12. And it starts to increase faster and faster. But that's limited by terminal velocity. Okay, so we can get the position, how far the skydiver has fallen at each of these time intervals. So it's kind of cool. Anyways, let me. So what are you guys going to do in your assignment? You're basically going to be changing this part for the dimensions of the problem. You're going to be changing the equation that you're actually solving for. Okay? And then what you're going to do is you are going to put the results array into a graph. So you're going to actually graph what the results look like. Okay? So I'm assuming you're going to have questions, so we will go to the Zoom room at this time.